Right. So welcome back after a long break here. I will remind you that the fifth problem set? Well, there was a problem set due just now, and there will be another one due next Wednesday that will just cover balloons and the story of today. Maybe a little bit into water distribution, but this will keep us busy for a little while. So to set the stage for today's topic, which is balloons, we've been following a thread of sort of the mechanical world all the way from skaters. Think back to that, the story of inertia and then how things move and how they accelerate in response to forces and how they have mass that resists acceleration and so on. And then we got more and more elaborate with the objects and with the stories about them. And so now this is a bit of a new thread. And when the new thread is the story of things that aren't solid. So everything up until now has basically been a solid. Now we're going to deal with things that are collectively called fluids that don't have fixed shapes. And the two fluids that you're most familiar with are liquids and gases. And so today is basically the story of gases. I mean, the physicist in me is thinking that as we're going to talk about balloons. And next topic will be water distribution, which is really in part sort of the story of liquids. Okay, so new thread, new issues to deal with, but a lot of stuff that relates to things we've already done. And so let me start off with a question, force you to have you drag stuff out of your backpacks. So there's the question. A helium balloon has a mass, and yet you know from playing with them, they don't fall to the floor. They typically will go up to the ceiling. Like, what's going on here? And so is there a real force pushing up on the helium balloon? You okay with the question? What's the question? What do you think? Oh, get rid of that. Well, I'll go to 30-second point and then come back. Four, three, two, 1, 0. Oh, come on. There it is. Hey, you guys are pretty well split. The majority going for yes. And yes is the right answer. There is a force pushing up on the balloon. And that makes, if you think about it, it makes sense because the balloon has mass. I mean, I'm telling you that. It's hard to appreciate it. You've never tried shaking a balloon in an environment where you really can tell, but it's got stuff in it. It's not like antimatter, or that it's not so exotic that it has no mass. It's got a mass. And we've seen already that things that have mass develop weight here near the surface of the Earth. So it's got a weight. It's got everything that all the stuff we've dealt with before has, just like a ball. But oddly enough, it floats upward. And for that to happen, when it's got a weight downward, it has to have some other force that not only balances its weight, but actually manages to exceed its weight upward and take it to the ceiling. And that's real. There is such a force. I had to, when I asked you a question long ago about when I throw a ball up in the air, does it have an upward force acting on it? I would, whenever possible, say, ignoring the air. And if you all remember that question, the answer was no, it had no other force. Neglecting the air, there's no force pushing up on the ball. It went up because of inertia. More sophisticated explanation, it went up because it had upward momentum. Just filling in new things we've learned since those early days. Now we're bringing air in. And air has influence on us. It doesn't influence us so much when you're just sitting there for reasons we'll understand shortly. But a helium balloon has so little weight that it doesn't take much of an upward force to cancel that weight and actually give the balloon a net upward force. And there is such a force. It's called the buoyant force. And part of the story of today is to explain why this force shows up. If you put something in the air, you all, for example, right now, you're immersed in the air is pushing up on you a little bit, not enough that it affects you, you can't sense it. But if you were a balloon, you'd be well aware of it. Okay? So that's this question. I'll turn it off. There actually is an upward force on things immersed in the air here near the surface of the Earth. All right. So to build up the story for why that, basically my goal is to help you understand why various types of balloons float. Not every balloon floats. You know the cartoon situation where the character blows up the balloon and then floats away. No, that's not going to happen. But it is possible to make balloons that actually weigh less than the buoyant force pushing up on them from the surrounding air, and they go up. And the two classic ways to do that are with hot air and with helium. All right? So how to start building the story here. Fluids are different enough from solids that they need some new physical quantities and ways of thinking about them. You know that when you push on something with your essentially solid hand on a solid surface, you can talk about the force you exert on it, and that force will have effects on it. For example, if there's nothing else pushing on it, it'll accelerate and all that stuff. Fluids, since they don't have fixed shapes, are a little difficult to deal with. Does air exert a force on something? Well, the answer is yes, it does, but there's a complication. It does push on things. For example, I will show you shortly. It's pushing simultaneously. It's pushing on the surface of this sheet of paper. It's also pushing on this sheet of paper. And it shouldn't surprise you to know that the force on this sheet of paper is bigger than the force on this sheet of paper. But it's the same air, so how do we describe how air pushes on things? It pushes on things in proportion to how much surface area it has to push on. So instead of talking about the force that air or any fluid exerts on something, it is customary and convenient, actually, to talk about how much force the air or any fluid exerts per unit of surface area, so that you can easily correct for the fact that this is bigger, more surface area than this. So we measure the way air and other fluids push on things in terms of pressure per force per surface area. That's known as pressure. So it's a familiar word. You've heard tell of pressure your whole lives. That's what pressure is. It's force per square inch, per square meter, per unit of surface area. And since force in the metric system, and I haven't dwelled much on units, but the unit of force in the metric system, the SI system, is the Newton. Remember, about the weight of a little apple? And the unit of surface area, and hopefully you're comfortable with area, is the square meter. So it's like it's a box, it's a square about like that, okay? So the unit of pressure is the Newton per square meter. And that has its own name, just to abbreviate it. It's called the Pascal, after Blaise Pascal, the philosopher and scientist. So pascals. Pascal is a Newton per square. 1 Pascal is 1 Newton per square meter. And that's a very small pressure, actually. It turns out the pressure that you're immersed in right now, and I'll show this shortly, you're immersed in the air. The air is pushing on everything in this room. It's pushing with a pressure of about 100,000 newtons per square meter, or 100,000 pascals. And that's a lot of force on a square meter of surface. That's a lot of overall force. 2 square meters, it's twice as much, and so on. So it turns out this is not a minor effect on life. I mean, normally you don't notice it, and we'll see why. Actually, I can show you why. This sheet of paper is currently experiencing a force. The air's pressure, I told you the air's pressure is this 100,000 pascals. This is, I'll say it's 1/10 of a square meter. It's probably not right, but it's 1/10. Then it's got 1/10 of a square meter. A whole meter would get 100,000 newtons, so this would get 10,000 newtons, which is about 2,000 pounds. 2,000 pounds of force from the air pushing like crazy on that surface. That's a lot of force. 2,000 pounds of force on this surface. You understand how I calculated that? Or questions about how I calculated that? Do I care whether you can calculate it? Not terribly, but if you've got 100,000 newtons on every square meter, and I've got 1/10 of a square meter, I get 1/10 of 100,000 newtons. 10,000, okay? Why the paper doesn't do anything interesting in response to that tremendous force on its left side is that there's an equal amount of force on the right side in the opposite direction. It's another surface. It's being pushed the other way. So when in most situations, the tremendous push on one surface is balanced by a tremendous push on the other surface. Okay? I've got leading to a number of demonstrations of these things, but I want to sort of build the story first a little bit. So one way of characterizing fluids is in terms of the pressure a fluid has, how hard it pushes on a surface per square unit of area. Another characteristic of fluid is how to deal with mass and weight. The mass of objects, we're used to them having a specific size and shape, and so they've got a certain mass. This ruler, for example, has a certain mass. Of course, how do I do it? Shake it. It develops a certain amount of weight as a result of having the mass due to the Earth's gravity, and so it's got a certain weight, and I can measure that weight by trying to support it at equilibrium and seeing how hard I have to push. Well, this ruler also has a certain mass and a certain weight, and they're both made of wood. So they're basically sort of the same material. One's just bigger than the other. And where I'm going with this is that how can we characterize the material from which these are made in analogy to how do we characterize the air that's here when the size is not so important to us? When we just want to know, we want to be able to describe where we're going, where I'm going, is I want to be able to describe the air, how to understand the mass of the air. And in analogy to how do you understand the mass of wood is to say, well, you can make a big piece of wood, a little piece of wood, and they'll have different masses, and that's clear and, it's interesting but not relevant at the moment. It's like, how do you just sort of get the mass of just the material? And the way you do that is to divide the mass of the object you're dealing with or thinking about by the volume of that object. So for example, this ruler has half the mass and half the weight of this one, but it's also got half the volume. So the mass per volume of this ruler is the same as the mass per volume of this one. That's just a characteristic of the wood. And that mass per volume is known as density. Another word that you've heard your whole lives, and so this is what density actually means, is it's pick a material you're dealing with and take the mass of a known volume and divide that mass by the volume you chose. So mass per volume, and the unit of volume in the SI system is the cubic meter. So it's a box, cube like this. All right? And things that you're used to, fluids you're used to having, what are their densities? Water has a density of about, and it's a mass, it's about 1,000 kilograms per cubic meter. That's pretty close. Yeah, 1,000 kilograms per cubic meter. So a box this big of water would have a tremendous mass. 1,000 kilograms would be hard to shake, It develops a lot of weight as well, of course, because the Earth's gravity, it weighs almost 10,000 newtons of water. And what else would I want to say? Okay, that's enough for water. How about air? You think like air is just nothing stuff. It's not nothing. Right around here, if I got a 1 meter box of the air in this room and figure out what its mass is, it would be about 1¼ kilograms. So the mass of a 1 cubic meter box of air here at the surface of the Earth is about 1¼ kilograms. So the density of ordinary air, that is mass per unit of volume, is about 1¼ kilograms per cubic meter. Okay? So at this point, what I want you to, what do I want you to know? What's the imperial unit of pressure? Or the American standard for pressure is the pound per square inch. It's again, a unit of force divided by a unit of surface area. And so the standard around here, in the US, instead of being the Newton per square meter, it is the pound force, or just the pound per square inch. And the atmosphere, atmospheric pressure, ordinary pressure, well, it's 100,000 newtons per square meter. That's equivalent to about just under 15 pounds per square inch. That's atmospheric pressure. All right? So what I want you to know at this point is fluids push on things by way of pressure. To figure out how hard they're pushing on an object, you typically then need to know what surface area it has, what surface area the fluid has available to it on which to push. That's pressure story. The density story is how much mass is there per unit of volume in the material. This applies to any material, and it can apply to solid materials. Steel, iron has a density of about 8,000 kilograms per cubic meter. Gold is somewhere up like 16,000 per cubic meter, and so on. It'll turn out that, well, when we get to some of the light gases, it's pretty dinky. Any questions about pressure and density, having sort of just talked about them for long enough? Let me start showing you some of the effects of pressure and density. I won't yet justify why there's pressure in the air down here, but I'll show you that it's here. And one way to show you it's here is by producing an imbalance in pressure. I told you that this sheet of paper is sort of oblivious to the pressure right now because there's a cancellation between the pressure acting on its left side and the pressure acting on its right side. But what happens if we take away the air and therefore the pressure on one side of that sheet of paper? It's going to then have an unbalanced force that's enormous. Well, I can't do it with a sheet of paper, but I can do it with this is sort of classic demonstration. This is a miniature version of what are known as the Magdeburg Hemispheres. So I forget who did this demonstration, but he had two half spheres of metal and a seal between them. When you put them together, they form a complete sphere, and there's a hole entering there through which you can remove the air. Okay? So the original ones were big enough that instead of people, and I'll want two of you all to do this, they used horses to try to pull them apart and found they couldn't do it. So can I have two people to come pull these apart, please? Come on down. Yeah. One more? One more. Yeah. All right. And remind me your name?
Sophia.
Sophia. And?
Diego.
Diego and Sophia. So right now, no sticky, right? They have, there's no reason why they would care about each other. But this is a device, this is a pump. Sorry, let's get started. This is a vacuum pump, and it's going to remove the air, and I got to sort of give you a reason for why that will work. Okay, and is it? Oh, okay, I didn't get a good seal. Now I've got a good seal. What this dial is measuring is the pressure inside the two spheres. It went from pushing as hard as the ordinary atmosphere whoosh, all the way down to not pushing nearly that hard. And now I can seal it. Turn off the pump. All right, so your job is to try to pull these two spheres apart. And people can do it. Some of you all can do it. It's really hard, but it's possible. Therefore, be prepared for it to come apart. Okay? All right, give it a try. So what's happening now is the outside air is pushing in on those two spheres so hard that it's about, it's a couple hundred pounds of inward force that they're having to undo. They're having to overwhelm. Not going to happen, right? Hold on to them. Let me let the air back in. Ready? Okay? Thank you guys. Yeah. Diego. Thanks. Yay. So, in keeping with the idea that this class is supposed to give away all the secrets, I want to make sure you understand why that worked. We took the air out from within the spheres, so there was no outward push due to the pressure. And the surface areas on which the pushing was taking place were tens of square inches. And using American units, if it's 15 pounds of push on every square inch, then you got tens of square inches. You got hundreds of pounds of outward force that's no longer there. The inward force is still present. And so the unbalanced pressures held those two spheres together very strongly. Any questions about the experiment? The Magdeburg Hemispheres? All right. So some of this in my mind begs the question, like, so where does the pressure come from in gases? In fact, what is a gas like? And a gas is a material in which the basic particles, those being atoms and molecules, and I can explain what I'll take a second in a moment about atoms and molecules. The basic particles are independent of one another. They spend very little time in contact and certainly very little time clinging to each other. They're just independent tiny little doobers bouncing around off each other. And they're moving about because of thermal energy. So the story of gases involves thermal energy inevitably. If there's no thermal energy, you don't have a gas. It's just going to clump up together and become a solid. So you need the thermal energy. And because of the thermal energy, you've got motion of these little tiny particles. They have primarily kinetic energy there's energy in their motion. They occasionally bump into stuff and briefly will store energy like bouncing balls. And we can sort of illustrate this, not with actual gas, because the particles are so dinky, they're exquisitely difficult to see. But we can pretend. So I want to do this. Is this going to work? Yes. What you are looking at up there on the screen is this device here where we're going to shake the bottom of a little container with little metal marbles in it. And as we shake that, and little metal marbles begin to have kinetic energy, you'll see that they hit each other and they bounce like bumper cars. They're transferring energy and momentum, and they push apart. They bounce off each other, and they actually can start to develop some pressure. And the pressure will show up in the act of lifting the lid. So that lid is not fixed in place. It can actually rise. Let me get in a reasonable position for this. Don't focus on me. Let me get out of the way and have it focus on the balls. But you can see the little particles bouncing off one another. They're independent of each other. They have the equivalent of thermal energy making them bounce around, and they develop pressure that pushes up on the little lid. And actually, if I turn up the jiggling, make it more aggressive, they push harder. So let me stop the fun and games here, come back to real life. Oh, I don't even need that. Okay, don't blink. All right. It's all set. I forget, I do various settings. I stopped using the cameras very much because if I take that camera, which is filming this class, and I move it to places, I tend to leave it in those places for the rest of the class. And so anybody watching the video of the class will see the demonstration, and then they will watch this demonstration sit there doing nothing for the next 30 minutes while I talk over here somewhere else. Anyhow, gases produce pressure by this thermal motion. The particles are bouncing around with thermal energy, and they hit surfaces. And whenever they hit surfaces, they transfer momentum to the surface. They hit it, they bounce off. Remember, that's a momentum transfer. And this relentless hitting and hitting and hitting and hitting transfers a steady dose of momentum into a surface of a fixed surface area. So pick a surface area, watch how many particles bounce off it and how much momentum each particle transfers. There'll be a steady force going on. Remember, momentum transfer is force times time. So in 1 second, a certain amount of momentum will be transferred to this surface area. And the next second, about the same, because statistically, you're going to get about the same number of hits. So ultimately, the source of pressure in gases is this relentless hitting, colliding of the particles themselves with surfaces. And in fact, they collide with each other, and so there's pressure and forces present in every portion of surface in the gas itself. So even in the air that I'm marking off right now, this air is pushing that way on that interface between the two parts, and the air over here is pushing the other way on it. So the pressure is present even if there are no surfaces. It's in the gas itself, that pushing. Is that okay? And the amount of pressure that the gas exerts depends on a couple things. It depends on the density of the gas, the density of the air. That is, how much mass per unit volume. If you double the density of air, and that's a feature that air has. Air, you can change the density of air. You can pack the particles more tightly and increase the mass per volume. It's hard to do with a liquid. That's one of the things that will distinguish a liquid from a gas. A liquid has a pretty fixed density. You can't take a cup of water and smash it and put a second cup in the same container and shove it in there. It won't do, you can't do, I mean, machines could conceivably do this, but it's extremely hard to do. Water is known as, and liquids in general are said to be incompressible. You can't pack them tighter. They want to be a certain density. Gas, not so much. You can change it. So if you double the density of the air in this room, if we did that, the pressure would double. Why? Because there would be about twice as many particles hitting every square inch of surface or square meter of surface. So it turns out that the pressure in a gas at the simplest level is proportional to the density. Is that okay? Can I give you an easy example? If you go up in altitude, we'll see the story behind altitude and the behavior of air. It's an important part of the story of why balloons float. But if you've gone into the mountains, you probably have noticed your ears popping and stuff like that, and other strange things happening. The air up there is less dense than it is down here. If you go high enough, it becomes a little hard to. You can physically breathe, but it's not doing you as much good. There's not as much oxygen per breath. So if you go onto Mount Everest, be careful. Density of the air up there is so small that it has difficulty supporting life. So density, you all have gone through various densities of air. They do vary, and with them the pressure varies, and they go pretty much 1-to-1. Double the density, double the pressure. Is that okay? Another question coming in here is, does that mean air pressure goes down when it gets cold? And the answer is yes. That's the other way to change the pressure of air. You can change it by changing the density, right? Pack the air particles more tightly, they hit more often, more pressure. You can also increase pressure by increasing temperature. So the thermal motion of every particle is more aggressive. It turns out that the thermal energy that any one of these little particles carries with it is pretty nearly exactly proportional to its temperature. Statistically, it's on average. So if you double the temperature of the gas, you double its pressure to a good approximation. Is that okay so far? But that brings up an important issue. What does it mean to double the temperature? It turns out pressure really does measure the kinetic energy per particle in a gas. It's a little more complicated in non-gases, and it can be a messy story. But as temperature goes up, the kinetic energy on average of the particles definitely goes up. And doubling the temperature definitely doubles the average kinetic energy of these particles. I promised also to say what the particles are. Atoms are the independent little guys with a nucleus and electrons whizzing around them, like neon. There's some neon, somewhere in my hand, there's some neon atoms. Like, I look around, there they are. They don't care about each other. Neon atoms don't stick to much of anything. They just are independent beasties. On the other hand, there are also some particles in there that are assembled out of a couple of atoms that do stick. For example, water. There's some water molecules in there, which, as you know, are H2O. They got 2 hydrogen atoms and 1 oxygen. They are stuck together. They travel as a team. It's very hard to get them apart. So they're whizzing along in there too. So air has got this mixture of nitrogen molecules, oxygen molecules, neon atoms, and such. They're bouncing around. Now, if I double their temperature, the pressure, I claim, will double. And that makes sense because the particles, when they got more kinetic energy, they're traveling faster, and they hit harder. So they hit the walls more often, and when they do hit, they pack more wallop, and so they transfer more momentum. And it turns out when all the dust settles of the calculation, the doubling the temperature doubles the pressure. But the issue is, what's the temperature? And you all are used to a couple of different scales of temperature. Fahrenheit is common in the States, and the Fahrenheit scale, it's an old historic scale. It has, what it feels like to get to about 0 Fahrenheit. That's pretty cold. It's about as cold as you get in the freezer in a modern refrigerator freezer. And 100 degrees is about body temperature, 98.6, whatever. So that scale. But you can go below 0 if you get a really super duper freezer or really bad weather. You can go above 100, no problem. You do it all the time in the oven. Fahrenheit. Celsius is another scale, which you can convert to one another and probably have. Celsius runs from 0, which is approximately the freezing point of water into ice, and 100 Celsius is about the boiling temperature of water into steam. But there are other scales, some of them historic and long gone, but there's an important type of scale that becomes relevant right now, and that is what's known as an absolute temperature scale, the metric one of which is called the Kelvin scale. What's an absolute scale? It's a scale where there's nothing below 0. 0 is the lowest temperature you can get to, period. And there exists such a thing. The lowest temperature you can get to is the temperature at which there is no further thermal energy to be extracted from a system. It's actually more a destination than, it's a goal rather than a destination. You can't get to absolute 0 for statistical reasons. It's like you can't roll snake eyes 1,000 million, billion, trillion times in a row. It's not going to happen statistically. Absolute 0 really is in principle when you've just removed every bit of thermal energy from a system. And it's as still as it can possibly be. No kinetic energy available, no potential energy available, gone. At that temperature is known generically as absolute 0. And absolute 0, you can figure out what it is in various temperature scales. In the Fahrenheit scale, it's about minus 459 degrees, pretty cold. In the Celsius scale, it's about minus 273 degrees. In the Kelvin scale, it's just 0. In the Kelvin scale, Kelvin scale is essentially a Celsius scale shifted such that it starts at 0. absolute zero. So you shift, the Kelvin scale is the Celsius scale shifted down 273 degrees. And if you go down towards that with ordinary air, its pressure drops. And so, okay, having talked to death on this, let's start doing some of these things. This being the first time of the semester to get out liquid nitrogen, any excuse to play with liquid nitrogen is a good excuse. So liquid nitrogen, so this is the same stuff you are currently breathing, minus the oxygen and some of the other little trace components. So it's just ordinary nitrogen, but it has been cooled down to the point where it stops being a gas. And I should say that the little nitrogen particles that are bouncing around here, you know, they exert pressure and all that stuff, they're independent of one another, almost. When they do bump into each other, they do show a little bit of stickiness, but at room temperature that you just don't notice it. You get them cold enough, they start to stick. And so this is so cold, they have begun to stick. So this is, yeah, what is this? It's about minus 300 Fahrenheit and about minus 195 Kelvin. I think that's right, yeah. So pretty cold, okay? And how do you make this? You run a refrigerator. We'll know how to make this stuff by the end of the semester. Just because I can, nice bouncy ball, okay? It did it. That's not my fault. That was the intention, however. So you take a nice handball and chill it down to that temperature, and it loses the molecular mobility that it used to have that made a rubber. And I'll come around the bench so I don't have to walk very far. Obviously, it's great stuff to play with, but you don't want to let it sit on your skin for very long. Oh, it's supposed to break. They make them too tough these days. Come back here, come back here. The other thing I almost got but didn't do was flowers. You put flowers in this stuff and then freeze them, and then you hit them and they just pss. Anyway, I'll let that guy cool for a second. Despite the fact that a big piece of rubber becomes pretty fragile, a little piece of rubber, amazingly enough, can tolerate that low temperature. So this balloon, what's holding that balloon open? It's got a little bit of elastic character to the skin. It wants to be small. It's being held out by a slight pressure imbalance between the air inside and the air outside. The air inside is a little higher in density and therefore a little higher in pressure than the surrounding air. That's what keeps the balloon inflated. We're not doing floaty yet. We're just come on, guy. One last time to see if I can bust this guy. Yes. All right. As I say, any excuse for liquid nitrogen is a good excuse. So this guy, if I put it in there, that pressure imbalance will be in trouble because the particles inside will slow down, hit less often, and it shrinks. Actually, it's a little bit of a cheat because it shrunk initially as the particles slow down, and then they start sticking to each other, and it actually turned into a liquid. So let me do this again with a gas that doesn't condense into a liquid by accident, and that is helium. Everybody should have helium around, right? Oh yeah, okay. Come on. Is it open? Just you got to know that it's helium, right? Okay, now I can talk. Come on. Okay, it's this, okay. It still doesn't sound right. Do I sound weird or not? No, I'm not sure. I'm not convinced. It's usually, oh, there we go. Okay, now I'm talking properly. Okay, the reason for the change when it works right is I gotta get out because it doesn't. Don't want to be like, ooh, okay, over I go. Helium, as we'll see, it's still the little particles in there bouncing around, but each particle is really little. It's got very little mass. It accelerates very easily, and as a result, sound travels fast in it because it's so responsive, so little mass in there. And sound travels faster, all the resonances in your voice shift up. Okay, I proved that it's helium, right? Okay, now, and I didn't pass out, also good. Okay, so now I'm inflating this with helium instead of air. The value of doing that is helium will not condense into a liquid at liquid nitrogen temperature. It scoffs at liquid nitrogen temperature. That's, warm day in the Bahamas. Okay, so you know what will happen if I let go of this, right? Okay, but I'm going to slow the particles down, the helium particles down. Unlike that balloon, which turned into a liquid inside and therefore got very, very small, this guy won't get very, very small. It'll get to about 1/4 of its original size. It has to crank up its density by a factor of 4 to compensate for its temperature having gone down by a factor of 4. So there it is, shrinky dink. And now as it warms up, it's getting bigger, and liftoff. See you later. So there has to be some advantage to air undergoing this strange transition to a liquid, which is sort of off topic, but why not? Because it transitions to a liquid when you put it into liquid nitrogen, it doesn't occupy very much space, and so you can inflate the balloon again. So here's the goal. I fill the balloon with air, and then I shrink, I reduce the pressure by lowering the temperature, and ultimately condense the air into liquid. And then I add more. And you can see where this can head, right? And it takes about 10 fills. So bear with me. 3, shrink, shrink, shrink. 4, 5, 6. If I stop early, it's always bad. You'll see why. Got to go to 7. So the molecules are they're slowing down. They're beginning to stick to each other. They roll around at the bottom as a liquid, and more molecules can come in and occupy the former space. Where am I? 8 now? I'm at 9. Okay, one more. Even I run out of patience. All right, and now if I don't really overfill it, it'll sit there for 5 minutes, and we'll all go like, when's it going to go? Oh, come on. I think I have to put it out of all of our misery. Ready? All right. So, pressure. It's the pressure of a gas depends on its density, depends on its temperature. One more good demonstration to do with this stuff. You'll remember this. Down the road, Marshmallow Man. So this is vaguely apropos of Ghostbusters, right? And I went for the biggest marshmallows ever. All right. Oh. Marshmallows are little bubbles, little sugar balloons. And you all are used to toasting them over a fire. When you do that, the temperature of the gas in those little balloons gets higher and pushes the balloon skin out. They puff, right? So that's the physics behind the puffing of marshmallow by cooking it. We can puff of marshmallow, not by cooking it, but by simply removing the air around it, so that there's a pressure imbalance between the pressure inside, which is at normal ambient pressure, and the no pressure outside. So here goes Marshmallow Man. I can zoom in on Marshmallow Man if I remember to do this. There you go, there's Marshmallow Man. All right, and now, we're taking the air out from around Marshmallow Man, and all the bubbles are getting bigger, just like balloons will get bigger. If I put a balloon inside that bell jar, it'll get bigger and bigger and pop. So he's bulking up here, but it's all ill-gotten gains, right? He's on some sort of juice. And the bubbles will eventually pop. It's very subtle. You can't see the bubbles pop. They just begin to leak. And then they reseal. And so Marshmallow Man might be at max bulk right now. And all the bubbles are now beginning to leak. The gas is coming out. And they're actually started fading. Let me turn off the pump and let the air go back in. So now I get the bubbles. They don't have much gas inside anymore. They're mostly empty. And now, oh, poor Marshmallow Man. All right. What else do I want to show you here? Okay. Yeah. All right. Go back to normal. Yeah, I guess it doesn't really matter. So there's air pressure. The air pressure imbalances do stuff. All right. I need to just one more piece of setting the stage for balloons floating, which we'll do next time clearly. But the setting the stage. Why is there air pressure? We know that the gas particles create air pressure by hitting and by colliding, the transferring momentum. Why is there air here at all? Like, why doesn't the air just like leave? And the answer is the air here at the surface of the Earth is held in place by gravity, the Earth's gravity, which happens, fortunately, to be strong enough to keep the air from leaving. Smaller planets don't. The gravity is too weak. So the moon, for example, if it ever had an atmosphere, lost it. Gravity wasn't enough. The thermal motion of the particles, eventually they just whizzed off into space and left, like little rocket ships. Off they go. So we've got the air here in place. It's pulled down by gravity. But then, okay, so why isn't it just like plastered on the surface of the ground? And the answer is because of that thermal motion again. The air particles here, in the absence of thermal motion, would be plastered on the ground. But as they bounce around, they lift each other up. And so the air down here, because of its thermal motion, is pushing on things. It's pushing the air up here up enough to support its weight. So the air up here is being supported by the air pressure down here. And the air up here is in turn supporting the air above it, which is in turn supporting the air above it, and so on. And if you start to think about what does the structure of the pressure have to be for that sort of arrangement to work, where the low air is holding up everything above it, which is holding up everything above it, and above it, and above it, it turns out you need to have what's called a gradient in pressure. It's got to change continuously. That's what a gradient means, from one value to another. And what's going on is the pressure down here, down low, is bigger than the pressure up high, because the pressure down low has to support more weight overhead. So there's a continuous shift in the pressure, and with it the density, and actually also the temperature from low to high. The pressure gets lower, the density gets lower, and the temperature gets lower as you go higher up. And this is familiar just from experience. You go into the mountains, there's less pressure, there's less density, and there's less temperature. It's this structuring that comes about from the need to support each portion of air supporting each other. And what we'll do next time is, on Monday, is come back and look at that gradient in pressure in particular leads to the buoyant force, the force that's holding that balloon up in the ceiling. And we know we're close, but we're not there yet. So have a good weekend and see you on Monday.